Hello everyone. My name is Juan Fraire, and in this talk I'm going to present routing in the space internet with contract graph routing. So without further ado, let's start. So we're going to see and cover a brief introduction and motivation on what actually brings us to talk about general space networks. And then we're going to go a little bit into detail on how can we abstract and create some models for this type of networks. And once we have the model in mind, then we're going to jump into directly what is contact graph routing and how this routing algorithm actually takes advantage of these specific models for space networks and actually also takes advantage of what is the operational concepts, the concepts of operation that is behind routing in space networks. And finally, we're going to terminate the talk by hinting about some trends and outlook for future research on the area. So, as an introduction, so we are living quite an interesting moment in space. We are having quite a successful missions that are showing very interesting enabling technologies. I'm just briefly mentioning some of them, like formation flying and intersatellite linking here. So we're seeing missions like Tango and Mango, missions like GOMEX-4 satellites, where very small satellites are actually able to fly together in a coordinated fashion and actually exchange data while this is happening. And some of these missions are also based on commercial off-the-shelf components, namely hardware and software even that is not originally thought to be used in space, but still this can be somehow adapted and screened so that high performance results can actually be obtained also in space missions. And basically this is brings us to the small sat paradigm where all these, let's say, more innovative principles and novel options are actually getting new applications into space as never before with lower price and cost than ever. So this also adds up to the fact that we're having reusable rockets and cheaper launches every day. So the cost of accessing space is becoming way lower. This actually brings us to the topic that we are start to having very amazing networked constellations of satellites in near Earth orbit. And just to mention SpaceX and many others that are flying around at the moment. So the trend is likely suggesting that this will grow in the future, and this naturally somehow spills into deep space exploration, where more and more missions are actually being based on CubeSats that somehow implements all this new space vision, where reusable components or conventional off-the-shelf components can actually already implement quite complex missions on very small spacecraft. The question is, how do we network all these missions? We're having an increasing number of assets in space, and having them connected by means of networking actually plays quite a lot in terms of reliable connectivity, in terms of resource sharing, and many other aspects, such as the internet did back here on Earth so many years ago. So the question is, how do we actually connect these type of networks? So if we see what are like classical mega constellations we're showing here on the left, then nodes tend to have quite a stable connection. I mean, it's dynamic in the sense that the nodes or the pair of nodes that are connected on a given moment basically evolves in time. So different neighbors actually appears, and this is a topology which changes in time and adapts dynamically to time, and somehow this can bring into place what are these type of mobile ad hoc networks routing protocols that has been already proven on some ground applications, on top of which the popular internet traffic control protocol or TCP/IP stack can be implemented. The thing that TCP protocols actually operates of what's called a telephony model, in the sense that the node, the source node, and the destination node of the flow of data has to be continuously connected to each other. There is no option for having a disruption on this network. However, as we start thinking on more challenging networks where the amount of satellites are reduced, or some networks that are sitting on outer space, delays and disruptions becomes the rule and not the exception. And in this type of networks, then TCP/IP are basically out. They cannot operate. But we need a different paradigm, which is called delay tolerant networking, where no instantaneous feedback is available or can be assumed. And also some storage of intermediate nodes needs to be implemented for keeping the data in transit over the node until subsequent links becomes available. So we say that DTN actually fits a different model, which is known as the epistolary model. So as I mentioned, the principle for delay tolerant networking, or DTN, are basically store, carry, and forward. The data can live for an arbitrary amount of times in memories on the nodes, namely satellites or spacecraft. And also the minimal end-to-end messaging is strongly suggested on this type of network because of the potential long delays faced by the links. So the architecture that actually implements this principle is known as, well, delay tolerant networking, and the way of enforcing or implementing these architectures on a protocol stack is by means of the bundle layer, which is implemented by means of the bundle protocol. The bundle layer is an overlay protocol that sits on top of potentially any other protocol, even including TCP/IP, as we mentioned previously. And the bundle layer, the bundle protocol, has been standardized on CCSDS, which is the Committee for Space Data Systems Connectivity, and also at IATF, which is the institution that standardizes Internet protocols. So the bundle protocol implementing this architecture naturally is in charge of the persistent storage that we were mentioning. This is in contrast with internet buffering, where data is basically not in the buffer for a short amount of time, but it can be kept on such a buffer for an arbitrarily long amount of time. Also, the bundle protocol specify how the data is encoded, and data in DTN is encoded into what's called bundles, which are basically bundle protocol data units. This is an example of how a DTN looks like, and the term overlay is here for a purpose. And you can see here a mission where we have some kind of mission control here on ground, which is connected by means of an internet link to a ground station, where an antenna and associated equipment are used to reach a satellite that, in this example, can be orbiting the moon, for instance. And then the satellite is in turn being able to connect to a rover, which is sitting on Mars in this example. So you can see that there is a DTN layer on top of all the protocol stack of these 4 nodes. And DTN operates over different families of underlying protocol links, namely TCP/IP. We have USLP from CCSDS. We can even have LTP and many other protocols. The trick is that these CLAs that are sitting on between the DTN and the underlying protocol, it is stand for convergence layer adapters, and these adapters actually takes care of adapting the bundle data unit to whatever protocol that's sitting underneath. And therefore, in this way, we can have an end-to-end connectivity on a delay tolerant way, where data may be able to sit an arbitrary amount of time on an intermediate node. And also the feedback from this data, namely an ACK or a confirmation of a receptions, is actually minimized on the DTN layer and only enabled on those links where there is a permanent connectivity, and this is only implemented by the underlying protocols that are already designed to operate in that context. So we have basically, there are several DTN implementations. 2 of them are highlighted for water space applications. So namely, Interplanetary Overlay Network, or ION, is likely the first and the most popular one, developed by JPL. And it's quite a full feature solution in terms that it assumes that you will run this on quite a reasonable microprocessor for space. This is in contrast with Microplanetary Communication Network, or MicroPCN, were developed by the Technical University of Dresden. They offer a lightweight expression of DTN, which much less featured, but much more streamlined for running on smaller microcontrollers. This protocol stack has been already flight-proof, proven on several missions, and also we have severe emulations and simulation tools that are available for the community for using and testing and doing research on these delayed networking protocols. So what is the concept of operations of routing in this type of networks? So we can say that we have three clearly distinct phases: planning, routing, and forwarding. So planning is a process by mean where a ground asset or a ground mission control center takes advantage of orbital propagators that basically informs on the location and trajectory of the spacecraft in space, which trajectory are they going to follow in the future, and combine this like with communications model being the simplest one, just a line of sight model, where you can determine who is going to see who in the future, and the start interval and the end interval of time where this connectivity is going to happen. This is the part coined planning, and the result of this phase is a contact plan that can be used for the next phase, which is routing. So these contact plans basically imprint the topology of the networks, and this information can be very valuable to answer the question of to whom should I send a given bundle of data at any given moment. And the way of answering these questions is by means of a routing algorithm. And one of the routing that is able to do this is contact graph routing, which is the routing solutions we're going to discuss today. Once we have the results of to whom should I send the data at any given moment, then I can construct what's called a routing table or a list of routes that satisfies it and can answer the question positively. And that information can then use on the third stage, which is the forwarding stage, on when the actual data is either generated locally or arrived from a given interface, then we use this routing table or this routing list and select among the routes on that list which is the one that we're going to use based on the actual information available at the node, namely the size of the bundle or even the size of the storage available at that moment. So to go a little bit into details on CGR, on contact graph routing, so the overall idea is to determine when and to which neighbor a bundle should be forwarded. And this is in contrast with opportunistic and probabilistic DTNs, where floating probability inference can play a very important role in answering these questions. In difference, in space DTN or scheduled DTNs, we have the option of using this contact plan data structure. This contact plan data structure, in principle, allows also to use some quite accurate theoretical models to answer such a question. So when should I forward something and to which neighbor should I do that? And there has been some works on MILP problems and optimal approaches to solve this question, but at the expense of computer processing, which unfortunately is not always available in spacecraft in computers. So an alternative and an algorithmic approach is CGR. So CGR is an algorithm that has demonstrated sufficient accuracy and efficiency to become kind of the de facto routing framework for space DTNs. And CGR basically record track is not so old actually. So it was first introduced in 2008, and since then it has received quite an intensive collaboration and cooperation from different researchers throughout the world. And now in 2019, CGR has been registered as a schedule-aware bundle routing book at the CCSDS, which basically standardize and can be used as a reference for implementing this routing algorithm in future space networks. So let's go into a little bit of the models and what is CGR assuming for making this routing calculation. So the main element in a model of DTN is the contact. So a contact is a time interval, basically between T1 and T2, which is expected that data will be transmitted by node A at a rate R, such that data will be received by a given node B in this case. So very simple concept. So basically, it's an interval of time where we're able to transmit data from one node to the other, and a series of these contacts, or a list of these contacts, builds and creates what is the contact plan, right? So basically, we have here one contact between 1, 2, and there is a node A and B, a source and destination pair. We have the start time, the end time. We have a rate at which data can be transmitted, and also a range defining how far away these nodes are. For instance, we can see that this contact plan that we have here actually describes the topology that we have here on the right. So you can see that we have, for instance, between D and E, we have 3 different contacts, and so on. Something that's interesting to say about contacts is that they are unidirectional. So you have seen from the previous example likely that one thing is to talk about the forward contact, and one thing is to talk about a return contact. This is contacts are not bidirectional. And the reason for this there is a reason for this actually. So the reason is that one of them is that the data rates for forward and return channels on space missions are typically heterogeneous. In this, we're not talking about such as Ethernet connections here on ground, where you have the same data rates on one direction than the other. So in order to properly model this effect in space, contacts are used on a unidirectional fashion. And as a result, you have a data uplink from, let's say, from ground to space, which is typically low rate, for example, a few kilobits per second. And then you might have an X-band transponder for the downlink, which can be much more capable, and we can be sustaining throughput of maybe in the order of hundreds of megabits per second. So another reason for this also is that because of this range, or this one light time, let's say this is the time light for from data originated at the source of the contact, how much time the data takes to arrive to the destination of that contact. This is a one-way light time metric. So because of this basically delay on the propagation, then the start time of a contact in one direction is not necessarily the same on the reverse channel. And this is something we can easily observe on this image on the right, where we have the ground station trying to contact a satellite B on a remote planet. And the ground station A is able to start transmitting data 5 seconds before the satellite B appears in the horizon. Why? Because these 5-second delays of propagation time actually allows enough time for satellite B to already be sitting on the horizon, and therefore catch the first bit of data from that stream of information. This is also happens the same thing on the return on the end of the contact. So the result, if we see the contact in a timeline, we see that A should start transmitting earlier than B, B should start transmitting later, but also B is able to keep transmitting a little bit more in the end as the contacts terminate. So this kind of time asymmetry also is captured by means of contacts, which, as I mentioned, has to be unidirectional in this type of network models. Regarding that data rate, so we mentioned that contacts have a constant rate variable that basically indicates on how much volume of data is going to be able to transmit it during that period of time. And these constant rates can even model variable rate throughout the contacts if you want to. And also, if you need to follow closely the evolution, let's say, of an adaptive coding and modulation scheme, then you can also use this contact model to have several contacts with different data rates, subsequent contacts with different data rates that can model such the varying data rate link in case if necessary. So basically, we have quite a good flexible element to model the connection. Now, how do we model the network? So this is the timeline view of the very same example we showed at the very beginning. So you can see actually a contact plan is quite a compressed expression of the connectivity of the network, which can be a little bit more complex when you see this on a timeline expression. And one immediate way of modeling from a graph perspective this type of connectivity is by means of time evolving graph, or TEG. Time evolving graph basically splits the time in discrete elements on which the connectivity, or the graph describing the connectivity of the network, remains stable. So in this case, we can say that we have a time time episode of 10 seconds on which the network remains stable. So you can see here also on the timeline view that every 10 seconds the network connectivity changes. This is for simplicity on the example, naturally not the general case. But the truth is that for each time episode that you have there, then you have a single graph that is able to describe your network connectivity during the time period. And therefore, what you can do is basically concatenate one graph after the other, and therefore you can have a network, a time evolving graph describing the connectivity of the network. The issue of TEGs is that it scales poorly, because as I have networks with more prolonged times, then the size of the data structure increases dramatically. The solution for this are contact graph. And as you mentioned, as you might imagine, contact graph is the constructive element of contact graph routing. Contact graph is a graph structure where the definition is actually quite straightforward. So we have a destination node D and a source node S in this example, and basically a directed acyclic graph, a contact graph from D to S is actually a set of vertex and edges, such that edges are the episodes of data retention and the vertices are the episodes of contact. So if you think of this is actually the inverse on how typical graph actually models networks, where actually vertices are the actual nodes and edges are actually the connections between these nodes. Now we are basically shifting this up, and we are saying that nodes nodes on this or vertices on this graph are actually the contacts on this contact plan, and the edges connecting these contacts here are actually the possibility of keeping data on a memory of an intermediate node. So therefore, for instance, we have this contact AB here and contact BC. This edge here between these two contacts is actually representing node B. This is node B playing the role of carrying the data from contact number 1 here to contact number 3. And by using this type of principle, then we can construct what is this graph expression of a time evolving network, but still the representation is fixed, is frozen in this stable graph. So the issue of this contact graph structure is that they are somehow not at all intuitive. Actually, this contact graph we are seeing here on the right is an example of a contact graph based on the same topology we have seen at the very beginning. So we can see that it has really no relation whatsoever with the topology at the first glance, but actually, if you look closely, then the contact plan that we have seen actually renders this contact graph, and basically node A can arrive to node E, starting by node B, or node C, or node E in this case, and so on. And there is a sequence of contacts that this data can follow such that it can arrive to the destination. And this concatenation of contacts are actually routes. And this is what we do care about in contact graph routing. So we have some examples in this case. So where route 1 in this case basically is a sequence of 3 contacts where data flows from A to C on an interval between 0 and 60, right? Then data flows from C to D on an interval of time between 0 and 30. And then finally data flow from D to E on an interval 0 to 10. So this is the red route we have here on this contact graph on the right. That means that data goes from A to C, from C to D, and from D to E as the final destination. So as you can see, all contacts in this route start at time 0. So this means that in theory, we could use this route with basically no non-data retention in any of the nodes. This is because this is assuming that obviously we generate the data at time 0. Okay. But as we are considering that each of these contacts is actually having a one time unit of delay, therefore, the best delivery time that this route can actually have is 3. And this is because the data flows over 3 contacts, each of which has 1 time unit of delays, whatever this unit is. This is just an example. And then also we have route 3, in which we do have actually here on route 3 this cyan color here, we do have a data retention and node D where the connection between D and E starts at time 30, and therefore the earliest time, arrival time from this route to the destination is 31. So the question is, how do we compute a route using this contact graph structure? Well, this is really straightforward, and this is one of the reasons of why contact graphs are so popular and actually are at the core of contact graph routing. And the reason is that Dijkstra shorter path algorithm can be easily adapted to run over this contact graph. I'm not going to go into the details of the algorithms, but with a slightly modified Dijkstra implementation of the shortest path algorithms, then a contact graph can be constructed on the fly for a given source and a given destination. So namely, there is a way of exploring the contact plan, which is basically a list of contacts, in such a way that during this exploration, you're actually constructing this contact graph, and you can explore the different structures so that you can execute what is called a contact review procedure at the beginning, and then a contact selection procedure. On the contact review procedure, what you're basically doing is just exploring the local contacts of your current contacts and actualizing all the variables, all the metrics that you need. The metrics we do care the most is the arrival time, naturally, that contact represents. And then once we have updated all these neighboring contacts metrics, then it's time to run the contact selection procedure to select which of these contacts is going to be the next chosen contact. By the end, once you, by this exploration, you will eventually explore a contact that leads to the final destination. And once you arrive to this final destination, then you are able to back propagate and construct a resulting route based on this Dijkstra computation. This is an example image of how this actually runs. So you have here the source contact, and this is where is the exploration area of the contact review procedure. You update the metrics for those contacts, and you proceed that way. And then you choose which is the next current contact on which you're going to be sitting on, which is this AB in this case. You explore, you update, then you select the next current contact. You explore, you update, and then this keeps running one iteration after the other until in your exploration phase you find a contact that is actually leading you to the destination. And once you arrive to the destination, you can back propagate and find which is the fastest route to arrive to that destination. So far so good. We can use this Dijkstra adaptation to compute a single route out of a contact graph. But actually, for the sake of truth, we can't make it with just one route. We actually need a list of them. So the reason of this is because, first of all, we're running a time-evolving network. So route expires. So routes are valid only for a given amount of time, which is basically the latest basically it's the soonest termination of all of the contacts in the route. Basically, there is one contact that is going to become limiting in terms of time, and you as a source node should send the data before that limit of time, and afterwards that route will become disabled. It was not going to be valid anymore. Also, routes have limited volume. So if they have limited volume, then they will get exhausted, and there you will likely need another route as well. We in DTN have priorities also on bundles. So it might happen that one route can be exhausted for a given traffic priority, and therefore it would mean that you need to use another one on the list as a secondary option. Also, we have uncertainties or failures on the routes that we have, so also having a backup route is also something necessary in DTNs. So how do we do this? So actually, the way of actually constructing a route list instead of a single route is by using several executions of the Dijkstra algorithm. We can see this here on the line 15 of this algorithm, which again, we don't have time to go into detail. I'm happy to help anyone that is interested on taking a look at this later. So the way of constructing this list is by means of the so-called Jens algorithm. So Yen's algorithm uses Dijkstra search in a nested loop, and the output of the algorithms is a list of k best routes, which is stored in this variable r in red color in this case. And interestingly, this set of best routes is basically a subset of potential routes, which this is a second list that is continuously populated by the Yen's algorithm, which up to k new routes on each iteration. And then at the end of that iteration, just the last best route from these potential routes is taken out and added to the k best routes list R in this case. And basically the Yen's algorithm terminates when you were able to find the k best route for this contact graph in particular. So as a result, instead of having a single best route for a contact graph, we are now able to compute a list of k best route for a contact graph and for a given moment. This is the result of the Yen's algorithm, which is actually part of the latest ION software for delayed networking. This is just some example of how Yen's algorithm operates on the same example network we saw at the very beginning. So we see that it first encounters a first route. This is stored as the best route on the red list, on the R list we have seen before. Then there is an exploration phase where a new potential route is found. This potential route eventually become part of this potential list, and there is a new potential route. This all happen on iteration 0. And then from those two potential routes, then there is one that becomes part of the main list. And therefore, at iteration 1, we already have two main routes to choose among. And as iterations continue, on each iteration, I basically discover one new best route for that list. And at the end, at iteration 6, I basically terminate my Yen's algorithm over this example with 1, 2, 3, 4, 5, 6, 7 potential routes to use from node A to node E. So now that we have all the list of potential routes, then the third phase, as we mentioned at the beginning, is the forwarding phase. So just to recap a little bit on this. So we have a first phase, which is the planning phase, where we construct the contact plan of the network. Then we have a second phase, which is the routing phase, on which we use contact graph routing, which leverage this contact graph data structure to compute a route list, as we have seen before. The third stage is the forwarding stage, on which we basically choose a candidate route among the candidate routes computed before, such that we implement that route to forward an actual data, an actual bundle that we currently have on memory. And this bundle can either be generated locally by the application on the node we are sitting on at the moment, or it can be generated by a remote node. So the forwarding phase is also a little bit tricky. It's not so straightforward. It's not just a matter of choosing the fastest route and using that one. And there are a few reasons for this. So first of all, you need to check the deadline of the bundle that you want to forward. So each bundle on DTN, as defined in the bundle layer protocol, has a deadline. This is a way of countermeasure congestion issues. So therefore, if the deadline arrives and this bundle is still being transmitted or stored at any local node storage, then it is perfectly fine to remove it from storage. So in the routing phase, this plays a crucial role because the route that you need to choose has to comply with that deadline. Namely, the data should arrive to the destination no later than that deadline. If the route is not complying with this deadline, then this route shall not be selected. Then the next item you will want to check also is what's called the earliest transmission opportunity, or ETO. And this basically accounts for which is the actual backlog of data that is sitting on your node at that moment. So the applicable backlog that you have actually is the amount of data that you have already enqueued for the first contact of that route. And this basically force you to transmit the bundle that you're currently evaluating later in time. So you want to understand when is actually the earliest transmission opportunity. If by any means this ETO is later than the termination time of the route, then this route shall not be considered either. Then a second item which is interesting to evaluate is what is the projected arrival time of this bundle. And this projected arrival time has to do with the earliest transmission opportunity for this bundle, and actually how much bandwidth this bundle is actually occupying on each of the subsequent contacts of the route. And this projected arrival time basically is what should be considered for the route. And by no means this arrival time should be later than the deadline and should be no later than the termination of the last contact of the route. Finally, you want to also evaluate which is the effective volume limit of that route, because it might happen also that you have already taken decisions to forward bundle through this route, and you are actually already occupying the volume resources available on that route. And basically, all these conditions need to be checked on forwarding time before declaring a route as a candidate from the list. So based on this, you can basically choose which is the best routing route for this. So naturally, you want to choose the one with the smallest projected arrival time. You want to choose as a second criteria the one with the least hop, with the fewest hops, and with the latest termination time. And finally, just to break a tie in case several routes actually delivers the same performance on the three prior items, then the smaller first hopper node ID should be chosen. Finally, just to mention, critical bundles are sent to every potential network, any potential node, any potential neighbor that you have, as this is a particular type of traffic in DTN. So finally, to conclude my talk, I want to mention a few trends and open topics for research and contact graph routing. One of them is for sure scalability. As you have seen, we have a Dijkstra routing algorithm that is adapted and called within dual nested for loop for the Jens algorithm as we have seen before. So scalability is by all means a concern on this, and actually these are some evaluations of scalability of contact graph routing on a very constrained onboard computer of a CubeSat. And we can see that actually when we're talking about thousands of contacts, the computation time that it can take to provide a viable result can scale to the order of seconds. This is not a huge problem in the sense that you typically have some good time to compute this route, but there is some implicances on the utilization of the processor that makes it difficult to argue in favor of running such an algorithm in very large scale networks. Secondly, uncertainty is also a big topic on contact graph routing computations because, as we all know, planning are not perfect. So this contact plan we construct at the very beginning of the concept of operations we have discussed might just not be perfect, and these are sometimes inaccurate. And also nodes fails in unexpected ways, which basically breaks all the assumption on where we are constructing this route that we have mentioned before. And this is a different area of research that's called uncertain contact planning or even opportunistic routing that tries to take care of these uncertain effects on the contact plan as well. And finally, congestion is definitely a hot topic because you want to be able to avoid overbooking contacts and storage of remote nodes, and you are in general have no way to know how data is being generated in other nodes or in a partition network such as the one we are talking about here for space. So these are three hot topics, interesting topics to do research on the domain. And I finally leave this slide here as potential consultation material and actually some links to describe in detail the algorithms we have seen before. So just also to provide some insight of those that are interested on. So this is all. I appreciate your time for listening. I also leave my contact information here for you if you have any questions. And I'm definitely open for questions. So thank you for listening.